Kia ora everyone, it's Bill here. Hey, what I want to have a look at is our analog to digital converter again. And this time I've got this little wee tiny thermistor here, this little bead thermistor connected to it. And at the moment you can see that I'm measuring 2.357 volts coming out of the voltage divider. So here's the voltage divider. Here, notice I've got the thermistor in the bottom half of the voltage divider. And I've got a 10K resistor here because this thermistor I bought is a 10K one, which means that at 25 degrees C, it has a characteristic of 10K ohms. Of course, these are non-linear. You can look at the graphs and the data sheets for this sort of thing. And then what I'm doing is I'm converting that to a voltage, and that voltage from the voltage divider is then converted to an ADC value. So what we're seeing is an ADC value of something from 0 to 1023, which represents temperature. So then what I've got to do is got to figure out how to convert this ADC value into temperature. And so the first part of that process, let's go and have a look at the actual code here. In my main program, I've got thermistor value equals 0. Let's just see this a bit. Thermistor value equals 0, and then I'm reading the value a number of times, number of samples times, which is actually set to 8 at the moment, and then I'm dividing it by that. So I'm taking 8 samples and then dividing it by 8 to get an average of 8. Then what I'm doing is I'm reading the trim pot value, and I'm going to use this trim pot value to offset the reading from the thermistor in case there's something different between that and what I might be reading on, for instance, my digital thermometer here, which says at the moment that it's 26 point, well, actually I'm touching the end of it, so it's around 28 degrees. It'll settle back down after a second. Now, what I'm going to do then is I'm going to show on the LEDs whether I've got an offset which is below or above this value. And at the moment, if you have a look up here on the output to teraterm, you can see that I'm showing 28.1 degrees and my actual temperature here is 28.8. So this I can then adjust by changing this value here. And you'll notice that when I go down below the exact value, I get that LED on, and as I go up above that exact value, I get the other LED on. So I'm going to set it to 28.3, which is about what the temperature is at the moment. It's just it's 28.1 now. So again, our little trim pot is a little bit, the backlash on it's a little bit difficult. I'm going to leave that. That's close enough at the moment. So I'm pretty close to actually my set point. And that way I can then calibrate my thermistor. Now remember that a thermistor has a negative temperature coefficient. It's not a straight line. So what I'm doing is I'm calibrating one point on this curve. And so that may not be very linear. Well, it won't be linear, but of course that change might not be consistent across the whole curve. Then what I've got to do is I've got to convert this ADC value back to a voltage, and then the voltage back to a thermistor resistance, and then I'm going to put the thermistor resistance into the Steinhart-Hart equation and actually work out what the temperature is, because that's the best way of doing this. So let's have a look at this. What have I got here? I've got simple ratio between VO, VCC, well, this resistance and this resistance is in a ratio to this voltage and this voltage here. So I'm just going to go RTH over 10K equals VO, which is this voltage, over VCC minus VO, which is this voltage here. So I'm just comparing this resistance and this voltage to this resistance and this voltage here. Okay, then I can come up with a nice simple formula for VT, for the now I know that my value here is 10K, so this is going to be 10,000 times V out over VCC minus VO. Now over here on my analog to digital converter, again it's a simple ratio. V in over my reference voltage equals my ADC value over 1023. And so my input voltage equals my voltage reference times my ADC value over 1023. And so what I have, of course, is I have a, what I'm looking for is I have this known here, and I have this unknown here. So I'm going to work backwards through this. And you can see in my code, as I go down here, so we look at my code, thermistor value, I'm doing the adjustment there for my calibration. And then I'm looking for tenths of degrees. I'm not going to use a decimal at this point. I'm just going to use this in tenths of degrees. And I'm going to convert my thermistor value to tenths of degrees using this function I've written, convert ADC to temperature. So let's have a look down here. We pass into it an ADC value. The ADC value at the moment will be, well, it's 2.357 volts on my voltmeter. VCC is about 4.8 volts. So that gives you an indication it's around that 500 mark. In fact, just a bit below it, 490, something like that. And I'm going to convert that to a float because I'm going to do a bunch of, I'm going to do some log in here to actually get this sorted. So the first thing I want to do is just work out that my, calculate the output of my voltage divider here. And so that's this line. And then I want to calculate what the thermistor resistance is. So that's this line here, calculate the resistance of the thermistor. And then I'm going to put it into this Steinhart-Hart equation. So let's just have a quick look at that. It's a model. Steinhart-Hart is a model for semiconductor at different temperatures. Actually, semiconductor resistance at temperatures, different temperatures. And the full model is this. I'm not going to use this. I'm going to use a simplified version of this. And the simplified version of this is when you know the beta parameter. And so the simplified beta model is 1 over T, or inverse temperature equals 1 over temperature at 0 degrees Kelvin plus 1 over my beta, natural log of the resistance over resistance at my known temperature. So let's just have a look and see what's going on here. I've got a nominal resistance value. These thermistors are a 10K thermistor. My ADC reference voltage is here. Now remember, I'm using VCC as my reference voltage, so it will actually compensate for any variation. I've just put a nominal value for ADC reference into my equations here. Nominal value of, well, let's just have a look up the top to see what I've actually used. Because it cancels out, I've used ADC reference voltage of 5. And let's see. And then we take the log of it, natural log of it. You need the math library for this. Put in this temperature coefficient. Now you get this from the manufacturer's data sheet. Now these particular thermistors that I bought are pretty cheap and nasty ones. Not a high quality one, possibly. It's hard to tell when you buy some equipment cheap on eBay or AliExpress or one of the other big suppliers. If you want something more accurate, then I've also found amongst my junk pile, I've got a little thermistor here which is sealed inside metal, and so this is submersible. I can put this in water, and it's got a little plug on the end. And I found that this one actually followed the manufacturer's data sheet quite well. So I'm going by the manufacturer's data sheet for this, and the temperature coefficient from that is 3950. And I can just see that I've put that in up here. There it is there, 3950. And if you have a bit of a read about this, you'll find how to do these calculations. Not hard, and what they mean. I won't go into a lot of the meaning here, I'll leave that for people who want to experiment. And then there's just the rest of those. And then what I do is I want to convert it to tenths of degrees, so multiply it by 10, and then I'm going to return an integer. And so that truncates any decimal places and just leaves me with, a couple of figures for temperature in tenths of degrees. And then what I'm doing is I'm sending that to my sendVal function. And in my sendVal function, what I'm doing is I'm playing around with that to insert a decimal point. And to do that, I'm looking at the length of the string. I'm pushing a 0 onto the end of this string. I'm going to make my string just a little bit longer. So for instance, my string might have, be 123 to represent 12.3 degrees. And so remember the character array will have 1, 2, 3 in it, but actual fact it will have 1, 2, 3, and then it will have a 0 on the end to say that that's the end. So what I do first of all is I look up the length of this, which is 3. Well, I find out that it's 3, and then I insert another 0 on my string because that's the new end of my null character, which is the end of my string. And then I push the 3 into here, and then I push a decimal point in here, and I leave everything else as it is. So even if I had a string of minus 5.4, what would happen is I would push another 0 in there, take the 4 and pop it in there. Well, actually, it would be 54 to show that it was 5.4 degrees, and then it would insert the 5 and then just leave the rest as it is. So that's how it would insert the 4 and then pop that decimal point there. So that's what this code here is doing. And then I'm sending it to my TerraTerm program. I thought that's really nice. Why don't we actually figure out if we can plot this somehow? And so what I've done is I've gone to Octave. Now Octave is a little bit like MATLAB. It's a free version of that, and I've written a script in Octave to plot some values. So I'll just open up that script. Here's my editor here for my script. So what this is doing here is, let's just maximize that a little bit. So first of all, in Octave, you need to load this package for instrument control, which allows you to control things on the COM ports. And then it looks to see if the serial exists, and it tells you if it isn't. And then it tries to close a port if it's already open, the one we're going to use. I found that sort of helped a little bit with my debugging at the beginning. I'm gonna plot 200 values, and then this is the line to actually open up COM15. So I know that I'm working with COM15 in my case. I'm setting up at 9600. And there's a little time delay here to wait for characters to come in. Then I need a couple of vectors or arrays, basically from 1 to 200 in the first one, and then the next one will be full of zeros. You'll be familiar with much of this language from looking at MATLAB. And then I open a plot window. I grab the handle to it, but I'm not actually using that. I give it some access and titles and some labels. And then when I get into this loop here, what happens is it reads the terminal S1, and then it's reading it looking for a carriage return, which is ASCII character 13. So if we go back to my code, remember what I'm sending out is I'm sending out my data here as a string, and then I'm sending carriage return a new line. So actually the 13 is a new line character, so it will get this /n or new line, and then it will know that it's got some data, and then it converts it to a double because of course it's an ASCII string, and that value there. What it does then is, if you can imagine the array is 200 characters long, it takes it just shifts every character in the array to the right by 1, and then inserts a new value in the first location in the array. Of course, vectors in Octaves do not start at 0 like arrays do in C, they start at 1. And then I've got to refresh my data and draw my window again. I put a little bit of a controlled exit in here. If I push the number 9, then I can break out of this while loop and then close the serial port and exit. So if I just, if I hit F5 for this, what happens then is it opens up my plot, there's my plot going on, and I'm doing a plot every half a second. That value is sent by, where's my delay up the top as a, there we go, macro there, I'm sending every half a second. And in my Octave terminal window over here, I will see that the current value is coming out of this. And this allows me then to just take my existing thermometer. Let me just pull my image to the foreground again. And oops, we won't go full screen on that. And I'm getting 27.1. And you can see that in my terminal here on Octave, I'm plotting 27.7. So I can just do a little bit of a wee tune on this. So I'm looking to make sure that I'm getting the same values, just a little adjustment. Again, I'm just calibrating a single point on this curve. So if you needed something more accurate than this, you would you'd do something better. That'll do. Rather than good enough accuracy. So there's my plot coming through. I'm recording the last 200 values. So at the moment, for instance, this air temperature, ambient temperature, 27.3. It's a warm bit of a day in my office. If I heat this thermistor up by putting my finger on it, you can see that the graph begins to rise as my body temperature heats up the thermistor, 31.9. And if I let go of it, there's a bit of thermal mass here, so it takes a little while for it to settle back down to its default value again. Hopefully this helps you understand a little bit about how we might use an analog to digital conversion process. And if you explore the code, have a look at it, and if you bought the components and they've arrived and you're able to build this up and experiment yourself, you can do some interesting things with this. Yeah, I hope this has been helpful to you. Cheers.